Hello, everyone. Welcome back. Okay, so now let's talk about how we predict polarity looking at the Lewis structure of a compound. Okay, so we can quantify the polarity by looking at where the dipole points. So a dipole is a separation of charge within the molecule. So one end of the molecule is partially positive charge, and the other end of the molecule is negatively charged. And that has to do with the fact that some molecules they will attract electrons more readily to themselves, and that's what we call something that's electronegative. So the electronegativity of atoms is what causes molecules to behave either as polar molecules or nonpolar molecules. And that's why water is particularly special because it's a very polar molecule despite only being made of a few atoms of only oxygen and hydrogen. Okay? So we draw a dipole. If you look at this arrow beneath HCl, the positive or the butt or positive end of the arrow is designated partial positive with the Greek letter delta, and the arrow is pointing where the electrons are going to flow in the molecule, so towards the more electronegative atom. So that's where the arrow gets the partial negative charge there. Okay, so here are some dipole moments of common compounds. As you see here, the more symmetric you are, the less of a dipole you have. So methanol, then carbon monoxide. I should say carbon dioxide, not carbo dioxide. Okay. And so symmetric molecules like CO2, they don't have a dipole, so that's why they're zero. And then as you go to less electronegative atoms, the dipole decreases. And you see here, water and methanol have two of the highest dipole moments, and they're commonly used as polar solvents for that purpose. Okay, so for the molecules we have here, let's draw the dipole moments, and let's state whether the molecule is overall polar or nonpolar. So we'll go into exactly how to do this. So let's draw CHCl3. Carbon is the central atom here. Hydrogen will be our one of the bonds, and then we have three chlorine atoms. So that's how chloroform should look. And if we draw the dipole moments, it's going to be pulling pretty much this way. So carbon's a little more electronegative than hydrogen, so we could draw the dipole this way. And then the dipoles are going to be pulled by the chlorine atoms here. And you see we have a net pull of electron density towards the chlorine atoms. So you don't have to worry about any vectors here. We're not going to worry about adding or subtracting vectors. But just think about the sum of the vectors here will be point towards the center of the chlorine atom on the right. So we could say this molecule is polar. And the reason is net dipole moment. It has a net dipole moment. Okay. So the reason for this is that not all atoms around carbon are the same. So even though this molecule looks symmetric, not all the bonds are the same, and when that happens, we're going to have a dipole moment. So not all atoms around carbon are the same, so this points to a dipole moment. All right? Let's talk now about CCl4. So CCl4, just like the molecule above it, chloroform, it's going to have instead now all the atoms are now chlorine. Now in this case, all the molecules are the same. All the bonds are the same, So it's going to be like methane, right? So it does not have a dipole. So if we look at the dipoles, right, we could draw them right here. The dipoles are going to be pulled in equal but opposite directions. And when that happens, they cancel out. So remember when we put a dipole and another dipole in the equal direction, their sum, so we add these together, right? Their sum is 0. So they have there's no net direction and there's no net magnitude. So when they're pulling in opposite directions, the dipoles cancel. So we're going to say here, dipoles cancel. Dipoles cancel, so we have a nonpolar molecule. So one criteria is that the bonds, to be nonpolar, the dipole moments of the bonds have to cancel out in equal and opposite directions. It just can't be symmetrical. Like chloroform looks symmetrical, right? I mean, you could draw a line horizontally, you could split the molecule in two, but it's actually not planar or how we flat like we drawn it. So we need to consider the actual bonds. So dipoles cancel, nonpolar molecule. Okay, so that's CCl4. Now let's look at this next molecule. This is called dichloromethane. So very popular organic solvent, although it's very toxic. So we don't like to use it if we can help it. So I'm going to draw dichloromethane a little bit differently here. So first I'll draw it how we usually draw it. CCl. Then we have H here and H here. So right now it looks symmetrical, right? The dipoles are pulling in equal and opposite directions, but this molecule is not flat like this. So this translates to this wedge and dash drawing, like so. So this is actually not a equal and opposite direction case. One is pointing away from us, and one is pointing behind the plane of the board. So that's what these dashed and wedge bonds mean. So they're pretty much non-opposite directions. So this is why I say, even though they're symmetrical, it's not going to be a non-polar situation because not all the bonds are the same. All the bonds have to be the same. Then you can say, okay, they must be cancel each other out. But if they're not all the same, they're not going to cancel each other out. So this is a polar molecule. Okay, dipoles do not cancel. All right, so that's DCM. Dichloromethane. So ammonia. So we drew ammonia earlier, right? And H. And here the dipoles are going to point towards the nitrogen. So they're all pointing towards the nitrogen. They don't cancel. So we say this is polar. And okay. So the lone pair actually attracts electrons. And that's because it's polarizing the protons. So the lone pair actually attracts more electron density. And that's because there's a partial positive being created between the nitrogen and hydrogen atoms. So the lone pair attracts electrons. So it may look symmetrical, but it's not. So this will reinforce the nitrogen atom. Okay, it reinforces the nitrogen atom. All right. So net dipole is greater than 0. Okay, so then in this way, the lone pair is on the nitrogen atom, is going to distort the electron cloud of nitrogen. So the nucleus is more attracted to the electrons from hydrogen, so it's going to pull the electrons towards itself. Okay. So this one has CO2, but we can do both. Let's do both CO2 and CO. Okay. So CO2, We know CO2's Lewis structure looks like this. It's 2 double bonds, 2 oxygen. And now we see that the dipole is going to point towards the oxygen because it's more electronegative. But now we have 2 equal dipoles, right? So this is nonpolar for CO2. Now let's look at CO. Remember CO, we could write it as this structure. So C, carbon plus oxygen, that's 4 plus 6, so 10 electrons. So we put the electrons here. And we see here that 2, 4, 6, 8. We have 10 electrons now. But now this dipole is going to be oriented towards the oxygen. So we no longer have a case where dipoles cancel because there's only one. So this is going to be polar molecule. A polar molecule, okay? So if we only have 2 atoms, as long as they're different, always polar. So molecule, molecule is always polar for any diatomic molecule with different atoms, okay? So no matter what the atoms are, so for example, HF, HCl, always polar because there's an electronegative atom and a less electronegative hydrogen or other atom. Okay. So I believe that is it for chapter 9, part 2. We talked about dipoles. Now I think about it, I thought we covered more more about dipoles, but I guess not. Maybe I'm thinking of something else. Okay. But anyway, that'll be it for chapter 9. So that's it for chapter 9, drawing Lewis structures, evaluating the shapes, and drawing dipole moments, and figure out if a molecule is polar or not. So this may have been familiar. If you took chemistry before, you probably definitely see the polarity of molecules. All right, so we're going to jump to the next bit here. So we're going to jump into chapter 10. All right, so just let me get my slides up here. Okay. So now we're going to chapter 10 now. So I'm going to exit out of here. And we're going to go to chapter 10. So chapter 10 is valence bond theory. Okay. So the first, chapter 9, we were talking about just drawing these structures. But now we're going to talk about how these bonds actually form now. Okay. So valence bond theory is one half of how we picture bonds occurring between covalently bonded molecules. So molecules that are between 2 nonmetals, or that don't involve the transfer of electrons, but the sharing of an unpaired electron in the highest occupied orbital, or the valence orbital. Okay. So these valence electrons, they interact with each other. They have to be oppositely spin. They can't be of the same spin because that's forbidden. When they combine to form a new bond, that bond will occupy a new orbital. A pair of electrons will occupy a new orbital, and it's not allowed that they can have the same spin. Remember in chapter 7, they can't have the same four quantum numbers. So that's the Pauli exclusion principle. That's strictly forbidden in the realm of quantum mechanics. Okay. So they have this what we call orbital overlap, and that the strength of the overlap determines the strength of the chemical bond. So the more overlap you have, the better the bond you form. Okay. Okay. For example, the hydrogen molecule, very simple. The most simplest compound you can have is formed from the direct overlap. So direct means they directly interact of 2 electrons and 1 s orbitals on 2 different hydrogen atoms with opposite spin. Okay? So let's use this approach to explain other bond types. Okay? For example, HF. So in this case, we have a hydrogen atom with 1 unpaired electron, and then the fluorine atom has 1 unpaired electron in the 2p sublevel right here. As we can see in this little diagram here. See now it has 1 unpaired electron. Okay. Okay, so the only difference is now the fluorine is going to use its 2p orbital. So we draw a 2p orbital for fluorine there, and hydrogen, and it's going to form this bond like so. And fluorine now will have a filled octet. So if we change it up a bit and think about 2 fluorine molecules or atoms interacting, they form bonds not from the s orbital, because remember, fluorine's s orbitals are filled. It's using its highest unoccupied orbital, which is one of the p orbitals. So they use the combination of 2 p orbitals. So you can have an sp or a p orbital bonding. So it doesn't matter which one it is, depending on what the atom has available. All right. Okay. Excuse me. Okay. So the result of this bond is, we call it the result of 2 orbitals overlapping. We call that a special kind of bond, and that's called a sigma bond. Okay, so sigma bonds are covalent bonds that are produced from the direct overlap between 2 atomic orbitals, H2, HF, and F2. They are called single bonds, and we call that sigma bonds because they look like an s orbital. If we were to view the bond on the axis for which it lies, it looks like an s orbital. So if you kind of look at this orbital here from a side view, it looks like a sphere. Okay. Pi bonds are a little bit different. They are formed when orbitals interact to form a new orbital that looks like a p orbital when viewed along the bond. So that's a pi bond. We'll talk more about pi bonds later on. So to kind of visualize these 2 examples, let's look at the oxygen molecule, O2. So looking at the electron configuration for the oxygen atom, it kind of tells us a few things. There are 2 unpaired electrons on each atom. If we look at them here, so one oxygen has 2 unpaired electrons. So let's assume that one of them is in the 2pz orbital and points towards the neighboring atom. Okay, so say another oxygen atom, right? This interaction, there's going to be an interaction between the 2 when they form a sigma bond, right? Okay. So this interaction between the 2 pz orbitals, they will lead to a sigma bond, as we see here, right? So these here are going to form a bond, and it becomes a sigma bond here. Okay. Right here. All right. However, we're left in a bit of a situation here. We have an unpaired electron on each of the 2p orbitals that are now, they're not on the axis where the sigma bond is formed. They're on the axis that's perpendicular to it. So it's either on the y or x axis. Okay. Yes, the y or x axis, because we made the z axis our horizontal. Okay. So imagine this is the z-axis here. So we're going to imagine this is an axis, and this is going to be our z direction. Okay. So you see here that on the PZ, this orbital now is very close to this orbital. Right? So there is an interaction here, okay? So instead of a sigma bond forming, this is called a Drew space interaction, or what we call side-by-side overlap. Okay, so this is what we call a side-by-side overlap. And this side-by-side overlap forms an interaction that's called a pi bond. So when you have parallel p orbitals parallel to each other that are not overlapping directly, that's called indirect overlap or side-to-side overlap, and that's what gives rise to a pi bond. So pi bonds, they're weaker than sigma bonds, but they still attract the nuclei from two adjacent atoms. So they form a attractive force, and that's why double bonds and triple bonds are typically much stronger to break, are harder to break than single bonds. And that's because they have this additional interaction from the perpendicular set of p orbitals on adjacent atoms right here. Okay? All right. Like so. So you see here, I highlighted in blue here, when these come together, we see these lines forming. So this is what I'm referring to as a pi bond. So these are pi bonds here. So let's write that in here. So this will be a pi bond. So this is a pi bond. This is the other part of the pi bond, because remember, the electrons can be either in the top lobe or the bottom half of the lobe, or at the same time. So both of these lines indicate the strength of the pi bond. Okay, and then if we look down here in a more simpler picture, this is what the interaction is saying. So you see here, this would be if we isolate the p orbitals here, we see the side-by-side overlap. And you see that overlap, it's not going to be as great of an overlap as here, but it's still an interaction that's important. And that gives rise to the strength of some bonds of some molecules. Okay? So if we have an oxygen molecule here, say we have the oxygen molecule, okay? So the single bond is the sigma bond. So the single bond is the sigma bond, and then we have the second bond here for the double bond. That's the pi bond, okay? So pi bond is the double bond, okay? It gives rise to the double bond in the structure. So the sigma bond gives rise to the first bond here. The pi bond accounts for the second one. And now if you have two sets of p orbitals that are available, you can have a triple bond too. So this explains why oxygen is sometimes written like this, as a double bond. And so we typically write it like this based on oxygen, the structure of oxygen and the availability of the half-filled p orbitals. Okay. All right. So let's stop here, and we'll pick up in the next video, drawing the Lewis structure and the description of bonding for the nitrogen molecule. All right. So I'll see everyone then.